Welcome back to our channel Samjho Simply. Today we are continuing our series on data structures and algorithms where we look into one of the most powerful tools in a developer's toolkit, Big O notation. In order to understand Big O notation, we'll take a few algorithms and analyze their efficiencies. First, let us take a look at an algorithm to calculate the sum of a given array. A naive method would be to start with our sum as 0 and then visit each element and add the value of the element to our sum. When any new element is added to the array, we repeat our method to calculate the sum and do the same when the element is deleted. Now, we'll try and build a formula for how much time this algorithm takes. Let n be the number of elements in the array, sc be the time to calculate a single sum, er be the time to read the value of an element, and finally sr be the time to read the value of the calculated sum. The amount of time needed to calculate the sum is the time needed to read the value of each element er plus the time needed to add this value to the sum sc. This process needs to be repeated for each element in the array, hence this quantity needs to be multiplied by n. And finally, we need to add the time needed to read the calculated sum SR. If you recall from our previous video, the time taken to access any given memory location is relatively small and can be considered as fixed. Similarly, the time required to calculate the sum is a constant. Finally, the time required to read the value of the sum is negligible. If we incorporate these, our formula can be simplified into some constant c times the length of the array n. You can now see that the time taken by this algorithm is proportional to the length of the array. Another way to say this is that the algorithm takes O of n in time. Let us look at a different way to calculate the sum. Rather than calculating the sum afresh every time we need it, we will keep a running total in a separate memory location. Now, when each element is added to the array, the value of the element is added to the running total. The value of the element will be deducted from the sum when an element is removed from the array. For calculating the formula for the time taken by this algorithm, let us assume the same variables. Since the actual addition to or subtraction from the sum is done when we insert to or delete from the array, the amount of time taken to get the sum is just the time taken to access the memory location holding the sum SR. As you can see, here the amount of time taken to get the sum is a constant. In Big O notation, we denote this as O of 1, where 1 is representing any arbitrary constant. Let us now look at a different requirement. For a given array, we need to calculate the sum of every pair of elements in the array. Here, the two arrows keep track of the two elements for which we are calculating the sum. We iterate through each pointer and calculate the sum of values indicated by the pointers. We end up with n square sums. For building the formula for the time taken by this algorithm, let n be the number of elements in the array, er be the time to read the value of an element, sc be the time to calculate a single sum, and finally sr be the time to read each of the calculated sums. Since the value of each element needs to be added to the value of each element of the array, the time taken by this algorithm is the number of elements n times the number of elements n times a sum of the time taken to read the value of the element er and the time taken to compute each sum sc. Finally, we need to add the time taken to read the sums. This will be n times n times the amount of time to read each sum sr. As we have seen with prior algorithms, ER, SC and SR can be considered as constant. We can update our formula as n square times a constant c1 plus n square times a constant c2. Simplifying this further, we can see that the time taken by this algorithm is some constant c times the square of the number of elements in the array. Hence, the time taken is proportional to the square of the length of the array. In big O notation, we call this O of n square. Finally, let us look at a common algorithm called a binary search. This is an algorithm we use often in life. For example, when searching for a specific word in a dictionary. Here, we have a sorted array in which we need to search for a specific element. Let us start with the middle element and compare it to the search element. Our search element is smaller than the value at the middle. Due to this, we can ignore the section of the array to the right of the index. We will repeat this process with the left section of the array. Comparing our search element with the value of the middle element, we can see that our search element is larger than the value at the index. Hence, we need to look at the right of the index, which is equal to our search element, and we have found our element. In order to calculate the time taken by our algorithm in the worst case, let us assume the following variables. Let n be the number of elements in the array, ER be the time taken to read the value of an element, and EC be the time taken to compare the value of an element to another value. Since each comparison divides the search space into half, the maximum number of comparisons needed is log n. The time taken in that case would be log n multiplied by a sum of the time taken to read the value of an element ER and EC, the time taken to compare two values. Simplifying this, our formula is a constant c times the log of the number of elements n. In other words, the time taken is proportional to the log of n. In big O notation, this is called O of log n. Big O notation provides us with a way to compare the performance of different algorithms. Specifically, it allows us to understand how an algorithm performs as the number of inputs increases. One way of understanding big O notation is to plot a graph. We'll have the number of inputs n on the x-axis and the time taken on the y-axis. On this graph, we can plot the various big O notations. The most common ones are O of 1, also known as constant time. This is where the time taken by the algorithm stays the same irrespective of the number of inputs. O of log n, also known as logarithmic scaling, where the time taken by the algorithm scales proportional to the log of the number of inputs. O of n, which is known as linear scaling. Here, the time taken scales proportionate to the number of inputs. And finally, O of n square, which is known as quadratic scaling, where the time taken scales proportionate to the square of the number of inputs. As you can see, with low number of inputs, these algorithms take relatively similar amounts of time. However, some of these would take drastically more time with higher number of inputs. Let us look at an example in order to understand why it is important to analyze how algorithms scale. Program A is written very well and functions with the efficiency of O of log n. Program B, on the other hand, isn't written so well and functions with the efficiency of O of n square. You test both of these with two inputs while testing. Let us say program A takes 1 millisecond to complete and program B takes 4 milliseconds to complete. Now, since the difference between the two is just 3 milliseconds, it feels like it is a minuscule, insignificant difference. Now, let us take a look at what would happen if each of these programs were put to use and we got 10 inputs instead of 2. Program A would take about 3 milliseconds for 10 inputs, and program B, on the other hand, would take 100 milliseconds. The difference of 97 milliseconds starts to show the level of inefficiency of program B. This level of inefficiency becomes even more glaring when we look at an example of 1,000 inputs. Program A would complete in about 10 milliseconds, whereas program B will take 1 million milliseconds. This difference works out to about 16 minutes and 40 seconds. Finally, here are a few things to remember about analyzing programs with Big O notation. First, while we've been talking about efficiency of programs in terms of time, the concept of Big O notation stays the same when we are analyzing how much memory space is being used by an algorithm. Second, when finding the Big O for an algorithm, we should be looking at the worst case performance. For instance, in our binary search algorithm, it is possible that we find our search element at the middle index, but we can't conclude that our algorithm is O of 1. Third, Big O notation only analyzes how the algorithm scales with respect to the number of inputs. It does not let us know the raw efficiency of a program. Two algorithms with the same Big O efficiency can and do perform differently. Finally, Big O doesn't take away the need for testing. Extensive real-world testing of your algorithms will still be extremely important. With this understanding of Big O notation, we can now dive into understanding the different data structures.